So in this problem, the problem is find minimum diameter after merging two trees. Lead code hard problem number 3203. So we're given two undirected trees, as you can see here. So they have n and m nodes numbered from 0 to n minus 1 and 0 to n minus 1 respectively. You're given two 2D integer arrays, edges 1 and edges 2 of lengths n minus 1 and n minus 1, where edges 1 of I is ai comma bi, which indicates that they have ai and bi, which are two nodes, have an edge between them in the first tree, and similarly for edges 2. So what we need to do is we need to connect one node from the first tree with another node from the second tree with an edge and return the minimum possible diameter of the resulting tree. Diameter, as you know, is the length of the longest path between any two nodes in the tree, right? So for example, in this example, we can obtain a diameter of 3 by connecting node 0 from the first tree and making an edge. So from here to here, when we make an edge, you see the longest path would be one edge, then 2 edge, and 3 edges. So the maximum diameter you can get is 3. Whether you choose this node or this node, you're going to get maximum of 3 diameter only. Sorry, minimum diameter, so that is going to be 3. Now in this example, you can see that we're given two trees and they're exactly the same. So how do we get the minimum diameter? We're going to be connecting the root node, which is here 0, and this 0. We're going to connect these two, and you see the maximum diameter is going to be 1 2 3 4 5. Sorry, yeah, 4 5 6. Yeah, so you can see we're going to get, let me explain to you. So the edge is this one, and therefore the maximum diameter you can get is 1 2 3 4 5. This is the, you can connect from 0 to 0. This is the best possible connection. And now moving a little below, we can see that we can go over the hints. So basically what we need to do is that, suppose that we connected node A in tree 1 with node B in tree 2. The diameter length of the resulting tree will be the largest of the following three values. Firstly, the diameter of tree 1, or the diameter of tree 2, or the length of longest path that starts at node A that is completely within tree 1 plus the length of longest path that starts at node B, which is completely within tree 2 plus 1. Now this plus 1 is added because it is basically the additional edge that we have added to connect the nodes from tree 1 to tree 2. Right. Now values 1 and 2 are constant regardless of our choice of A and B. So these two values, a diameter of 1 and 2, these are constant. Therefore, we need to pick A and B in such a way that minimizes the value 3, right? And finally, we have a hint, that is, if we pick up A and B optimally, they will be in the diameters of tree 1 and tree 2 respectively. Exactly which nodes of the diameter should we pick? Which nodes should we pick? So we see that A is the center of the diameter of tree 1 and B is the center of diameter of tree 2. So we need to find the centers essentially. So now going over to the solution, how you're gonna be performing it. Firstly, let me go over to the editorial to show you exactly how it's going to be working out. So what we need to do is to select nodes. It is crucial for us to minimize the overall diameter. Like we aim to select those nodes so that if chosen as roots, the heights of their respective trees are minimized. In practice, we often involve selecting nodes near the center of the tree, ensuring the subtrees are as balanced as possible. So the first approach is farthest of farthest, which is BFS. So we observe that any tree can be seen as a sequence of nodes on the diameter itself, plus the additional subtrees branching out from the nodes along the diameter, as you can see in this picture, right? So we have a sequence of nodes along the diameter and some additional subtrees branching out from the nodes along the diameter. So for any node in the tree, its minimum distance to one of the diameter's endpoints, say A and B, is always going to be less than or equal to the diameter. This can be proven by a contradiction. If one endpoint of the diameter A is known, the other endpoint B is simply the farthest node from A. So based on that, a naive way to find the diameter is assume that each node is one endpoint of the diameter, then calculate the farthest node from it and record the longest path. But this leads to a time complexity of O of n square, which will result in TLE. So we're going to be going over to the optimized approach. So we observe that we only need to find the farthest node of a single arbitrary node U, and that node would be one of the endpoints of the diameter. So the case one is U lies on the diameter. Running a BFS for the longest path from U will find an endpoint on the diameter. Case 2 is U does not lie on the diameter. The path from U to the farthest node passes through the diameter, so the problem reduces to case 1 itself. Now, to calculate the diameter of a tree, only two BFS calls would be required. First BFS starting from any arbitrary node to find the farthest node from it, which is also an endpoint of the diameter. And the second BFS starting from this farthest node to find the farthest node from it, which is equal to the second endpoint of the diameter. So now going over to the algorithm, what we are going to perform. So we have the function minimum diameter after merge. We need to calculate the number of nodes for each tree. N is the number of nodes in tree 1 and M is the number of nodes in tree 2. Then we build adjacency list for both trees. So we call build adjacency list n, edges 1 to construct the adjacency list for first tree, and build adjacency list for m, edges 2 to construct for the second tree. Then we can calculate the diameters of both trees. So we call the function find diameter. Then we get the longest path that spans across both trees. So we calculate combined diameter as the sum of half the diameters of both trees plus 1, which is rounded up. and then we return the maximum of the three possibilities, and then we basically have the two functions. So I'll explain to you uh, as we go along the solution.